In this video, we'll learn how to calculate the heat of formation. When we think about a heat of formation, what we're really talking about is the enthalpies of formation. So remember, an enthalpy of formation is defined as an enthalpy change for a reaction in which exactly 1 mole of compound is made from its elements in their elemental form. So this is 1 mole of any compound being made from its elements. And the standard enthalpies of formation are known as delta H, subscript F with the 0 at the top, which is known as a naught. So delta H naught are measured under standard conditions. So when we're talking about components made from their elemental forms, that'd be something, let's say we want to create methane, CH4. That'll be made from 2 hydrogens in their gas state, because that's hydrogen's elemental form. It always comes as H2, plus carbon in its graphite state, because that's carbon's natural form is carbon graphite. So if I look up the enthalpy of carbon graphite and the enthalpy of hydrogen, adding those two together will give me the heat of formation, or how much energy it takes to create methane. Let's say methane's a gas at this point. And so if we remember those standard state conditions are denoted by the naught symbol. That means we're in standard state. If you don't see this, then you're probably not in standard state, or the person forgot to write it. So in standard state, gases and liquids are in their pure form. So that means we're talking about H2 as a gas, or if we're talking about a liquid, we could have water in its liquid form. Gases are at a pressure of 1 atmosphere. The temperature is 25 degrees Celsius. And concentration of any aqueous solution is 1 molar. And so the standard state enthalpy of formation is the most stable form of any element. And the standard enthalpy of formation for any element is 0. When we're looking at some standard enthalpies of formation, we can see different compounds here. Like let's say we look at acetylene, C2H2, has a delta H of formation of 226.7 kilojoules per mole. So we have to add in 226.7 kilojoules a mole to get acetylene from its elemental form. So if I get acetylene from its individual elements, again, that'd be our carbon graphite, plus 2 of those, H2 in its gas state, combined together to give you acetylene in a gas. So what that delta H is saying is I need to add in that 226.7 kilojoules of energy in order to form this from my starting material here. And so we can use this delta H of formation and these tables to obtain the delta H of a reaction for any reaction of interest. We don't actually have to run that reaction anymore. We can just add up the enthalpies of formation. And so if you remember when we were talking about Hess's law, we can add different equations together that have a known delta H value and come up with the delta H for a new reaction. We can also use our heats of formation to come up with our delta H is the sum of the heat of formation of the products minus the sum of the heat of formations of the reactants. See, and I forgot that 0 right there. And so N and M here, so N and M are the coefficients from the balanced equation. So if we look at our reaction here, let's say we're taking propane and oxygen, and I want to create carbon dioxide and water. So if we remember, that was our C3H8 plus 5 O2s, all in the gas state, gives you CO2 plus 4 waters. And so when we have our balanced equation here, the coefficients here, the 1, the 5, the 3, and the 4, those are the N's and M's. And so what you can do is you can run the different equations here, add them up to get your products, get your delta H of reaction. Or I can just figure out, going from the compounds here straight to the products, what that would be. So let's say we want to calculate our delta H using our heats of formation, because we don't have the delta H for these individual reactions. For that, we go to our table and we'd start looking it up. So for carbon dioxide, it's negative 393.5 kilojoules. And there's a 3 in front, just like there's a 3 there. Water from our table is negative 285.8 kilojoules. And since we have 4 here, we have a 4 here. Propane is negative 103.85 kilojoules. And oxygen, since this is oxygen's elemental form, it has a heat of formation of 0. So then I just sum up these two parts here, my products, my reactants, and when you add them all together, you get negative 2,219.9 kilojoules, or we can say it's negative 2,220 kilojoules. So even if I didn't have the delta H1, delta H2, delta H3, I can still figure out the overall delta H of reaction here by adding up the heats of formations for the products and reactants. And so now I'm making sure you have your thermodynamic tables available ready for you. Let's practice. So make sure you have your thermodynamic tables right next to you so you can use them for these types of problems. So if we want to calculate the heat of formation for combustion of liquid ethanol in air to form carbon dioxide and liquid water. So since I'm saying calculate the heat of formation, that's when I know I have to use those thermodynamic tables. And so the first step is we need to write our balanced equation. So if we write our balanced equation, we have ethanol, C2H6O, plus oxygen, because it's a combustion reaction, so I know I have to have oxygen, carbon dioxide, and liquid water. So remember, we got to look at the state of the matter. Water liquid and water gas and water solid all have different enthalpies. So we want to make sure we look up water liquid. So since we need to calculate heat of formation, that's when we're going to use our delta H equals the sum of the delta H's for the products minus the sum of the delta H's for the reactants. So once we look at these delta H's, you should end up with, for carbon dioxide, minus 393.5 kilojoules. For liquid water was again minus 285.8 kilojoules. For ethanol, it's negative 277.7. And oxygen, since it's in its elemental form, 0. Once we add it all up, we should end up with about negative 1,366.7 kilojoules per mole of energy. So this is how much energy is released in the combustion of ethanol. And since our delta H is negative, we know it has to be exothermic. And that makes sense from what we know about combustion reactions. Combustion reactions give off a lot of heat. So a lot of that heat is exiting the system. And so now you should be able to calculate your delta H's of formation using your thermodynamic tables. Remember, all you have to do is look up the compound on the table, make sure it's in the correct state, whether it's a gas, liquid, or solid. And then we just use our equation here to sum up the delta H's of the products minus the delta H's of the reactants.